Hi everyone, this video is going to be me going over some problems from section 1.4 and 1.5, but before I get into those problems I want to talk about a few things that I'm going to be using to solve these problems. The first of which is this idea that the cross product of any two vectors on the plane will result in a normal vector. So way back when we first talked about the cross product, I said that A crossed with B creates a vector that is perpendicular to both A and B. So here's A and B, and then A crossed B is perpendicular to them. What you may have noticed is that if you have two vectors like A and B that are on the plane, then this A cross B is acting like a normal vector on there. So we can say in general, the cross product of any two vectors on the plane will result in a normal vector, and we'll be using that idea a lot in here. So two vectors on the plane, cross product gives us a normal vector. One note to make about this is you might get instead this normal vector here. You might get this normal vector here, right, depending on which vectors on the plane you use, but you'll always get a normal vector, right, something that you can use to define the plane. Another note that I'll make here is that visually I like to show all three of these vectors lining up so that I can show you the 90-degree angle, but I can pick this vector on the plane and I can pick this vector on the plane, and they don't have to line up. Remember that vectors only have a magnitude and a direction. They don't have a position. So we'll see an example of that where we use a vector that don't line up like that in our example. The second thing I want to show you, since you'll be doing something like probably at least 6 cross products during the exam that you have coming up at the end of the month, I've decided to let you use GeoGebra to calculate the cross product. My thought is I'm more concerned with having you know how to understand the concepts of planes and plane geometry than I am with the computation of this cross product. So that's what I'm going to be using to find my cross products. But if you go to GeoGebra, where you would normally type in things like your arc cosine and things like that we're using, so in that algebra tab, if you type cross and then these parentheses, and then your two vectors separated by a comma on there, that will tell you what the cross product of those two vectors is. Okay, so let's get started with this problem here. So it says, which of the following planes describes equations describes a plane through the points P, Q, and R. What I sometimes see people do, their first instinct is to try and maybe graph these either in GeoGebra or in 3D space and try to figure out where exactly these points are, 0, 0, 1, 1, -2, -6, and then try to make a plane out of that. For these types of problems, we really don't need to know where exactly these points are. In fact, we can just draw a really, really generic picture, I think is the best thing we can do, is just draw our plane. I like to draw it, kind of three-dimensional looking, but you can draw it flat if you like, and then just knowing that it's got 3 points, P, Q, and R. Now, if we want the equation of a plane, And looking at these equation options that we have over here, these are all of the form, that second form that we learned, ax plus by plus cd, cz is equal to 0, or d rather. We've got that form of the equation, which looks like we have here, but just to refresh your memory, we've also got this form. Right, this was the other form we worked with a lot. But these equations for the plane, they need two pieces of information. We need ABC, which is our normal vector, and we need some point on the plane, x naught, y naught, z naught. All right. So for a normal vector, all right, that's our ABC, and our point, x naught, y naught, z naught. For our point on the plane, p naught, any of these points will work, right? We just need a point on the plane. I'll end up using p later on. So that's taken care of, right? We know what p naught is, but we need to find this normal vector. I showed you here that if we have two vectors on the plane, then we can create a normal vector by taking the cross product of those two vectors. We aren't given two vectors on this plane, but we are given 3 points. And if we have 3 points on the plane, we can actually create those two vectors. So here's one vector, PR, and here's another vector, PQ. So the idea is I've got two vectors on the plane. If I can figure out what these vectors are and then take their cross product, that'll give me my normal vector. And then I'll have a normal vector point. I can figure out my equation. Okay. So let's figure out first of all what those vectors are. So I'm going to give them some names. I've got PR. And the way that you create a vector from 2 points is you take all the components from the tip and you subtract them from the tail. Right? We're trying to figure out not a slope per se, but how far are we traveling in the x, y, and z direction. So this is going to be 3 minus 0. -5 minus 0, and -3 minus 1. Right? All the points from the tip minus all the points from the tail. So that's going to be 3, -5, -4. Okay. My next vector is the second one here, PQ. So PQ is going to be tip minus tail. So I've got 1 minus 0, -2 minus 0, and -6 minus 1. I could have chosen a lot of different vectors here. I like using, anytime there's a 0 in there, I use that point as much as possible, right? But I could have picked this vector. I could have picked QR. I could have picked RP instead, right? Lots of options there. But this one is going to be 1, -2, -7. Okay. So these two vectors, next up is taking the cross product of those two vectors to get our normal vector. So that normal vector is going to be PR crossed with PQ. I'm going to take that over to GeoGebra and type in cross those two vectors. And I've already done that ahead of time, but what I get there is 27, 17, negative 1. Positive 27, positive 17, negative 1. And that's my normal vector, right? Taking the cross product of those two gives me a vector that's perpendicular to both of them. So that's my normal vector. Depending on what vectors you used, you might get a different normal vector. For example, you might have gotten negative 1 times this, right? Something that's parallel to that normal vector, right? But not quite the normal vector that we got. So you may have gotten negative 27, negative 17, positive 1. You may have gotten negative 54, negative 34, 2, right? Double that, or any number, any scalar number times that normal vector that you got. The reason I'm mentioning these is because if we look at our answer choices over here, these are all in the form AB. Ax plus by plus cz is equal to some number. So now that we have our normal vector, 27, 17, negative 1, we should be looking out for that a, b, c, right? Since those are the components of our normal vector. Just looking down the list, I see something that's close here, right? I see negative 27, negative 17, and then positive 1 sort of hiding there. That's not the normal vector that we got, but it is negative 1 times that. So a couple points of caution here. You should definitely be looking out for any scalar, any parallel vectors, right? Definitely looking for any scalars of your normal vector that you find in this equation here, right? Because you might get something different. Another thing to look out for is just because you find your normal vector here, that doesn't mean that you found the correct answer here. So I would, in this case, you've got the numbers 27, 17, and negative 1. That 17 is prime number, so you're not really going to be finding anything, reduced. You're not going to find a reduced version of that like you might get if you had negative 27, 9, negative 9, right? Where you could divide everything by 9 and maybe look for that one. Anyway, point of caution, think about the parallel vectors, right? Because you might see the parallel form in there. We also are not guaranteed that this is the right answer. I think given the answer choices, we've got a pretty good shot at getting this right if we guess this one that has the right normal vector. But maybe we're missing something here. Maybe we had some calculation error here. So the way to double check it is to check this d value. So remember that d in this context, we've got ax plus by plus cz is equal to d. D is equal to ax naught plus by naught plus cz naught. And when we go ahead and plug in our a, b, and c, we definitely want to use, since we're using this negative 27, negative 17, positive 1, we want to use this vector specifically. Right? We're going to use this one to check d because that's how it appears in this equation here. Okay. So that's going to be our ABC, is negative 27, negative 17, 1. And our point is going to be, again, any point on the plane I'm going to choose P because it's got 0, 0, 1. But any of these points, if we've done this correctly, any of these points should give us that 1 value. But I'm going to choose P. So I'm going to use P here. So D is going to be equal to negative 27 times x naught, which is 0, plus negative 17 times 0, plus positive 1 times z naught, which is positive 1. So all that together is 0 plus 0 plus 1 is equal to 1. Okay, good. So we plugged in our point using this normal vector as it appears in this equation, and we got 1. So we can be confident that we got the right answer here. Okay. Again, big skill set from this one. 2 vectors on the plane, however you can create them, that will give you that normal vector if you cross them. Okay. So let's use that same technique to figure this one out. This one says plane 1 is the plane containing these 3 points, and plane 2 is the plane containing DEF. Find the smaller dihedral angle between the planes plane 1 and plane 2. Okay. Again, I'm going to draw a very abstract picture here to talk about these 2 planes. So I'll call this plane 1, and I'll call this plane 2. Right. Remember, it may be, when they say that smaller dihedral angle, it may be this one here, but it may be the supplement, right, of that. So we'll just keep that in mind. If we get something like 120 degrees, then we'll know that we want to subtract that from 180. Okay, so plane 1 has these points. I'm not concerned about their coordinates quite yet. I'm just drawing an abstract picture. So I've got A, B, C, plane 2, D, E, F. Okay. Same exact idea, right? Like I made the argument that if you have 2 planes and you take their normal vectors, right? So here's plane 1, here's plane 2, here's this normal vector sticking out of it. If you can find the angle between the normal vectors, you can find the angle between the planes, right? So the angle between these, these normal vectors will be this theta, and we just need to find out the normal vectors. We're going to use that exact same technique from last time. So I'm going to pick 2 vectors on plane 1. That's going to be vector AB and AC. And then just to show you that you can pick these in any order, I'm just going to intentionally choose a sort of weird configuration. I'm going to look at DE, and then I'm going to look at FD. Right, just to show you that it doesn't have to have this nice tails matching setup here that we have. Okay, so I'm going to go a little quicker through the work now that we've got the setup here, but I'll split up my work and say here's for plane 1, we've got 2 vectors. We've got AB, which is equal to 5 minus 0, 3 minus 2, 0 minus 0. You can probably do a lot of this in your head, right? And if this step seems a little unnecessary, then you don't have to do it. But I will say that this will save you if you end up computing something wrong. It's a lot easier to go back and look at what you've done. And try to see where a mistake happened. Right? Okay, so let's see. This one's 5, 1, 0. This vector is 1, -8, +2. Just going to double check that I'm still recording. Okay. If I want to take the cross product of those two to get my normal vector, I'm going to call this n1. So my normal vector will cross AB with AC. Again, the order of these two doesn't matter. If you switch the order of these two, then that would just be -1 times that vector, right? Still a normal vector, just the opposite direction. Okay. So this cross product, again, I did this ahead of time in GeoGebra. So for this one, I get +2, -10, and -41. Same thing for plane 2. dE is going to be equal to E minus D. So this one's going to be 0 minus -4, -3 minus 2. Just double checking there. Okay. 2 minus 3. So that'll be 4, -5, -1. And then FD. So this will be these components from D minus these components from F. -4 minus 6. 2 minus 1. 3 minus 6. Oh, see? Just double checking here, right? I had 3 minus -6. So really that should be a plus there. So 3 minus -6, that'll be a +9 there. All right. Taking the cross product of these two will give me this normal vector sticking out of plane 2. DE crossed with FD. So that'll be something I plug into GeoGebra, and that'll give me -44, -26, -46. If you miss, the joy of determinants, you can always do these cross products by hand. But again, you do have that option, just typing them in using this notation, right? And you'll be doing a lot of them, so I trust that everyone here has done them at some point. So, okay. normal vector, normal vector. Let's find the angle between those normal vectors. We're using this formula. Sine of theta is equal to angle between two vectors. So this is a important one to commit to memory. So it's going to be the dot product divided by the magnitudes. I think the easiest way to organize this work is to figure out the dot product, figure out the magnitude, and then put everything in there. So that's how I'm going to organize my work this time around. But I'll be using this formula here. So let's see, n1 dot n2 is going to be equal to, let's see, 2 times, so dot product is the sum of the product of corresponding components. So 2 times negative 44 plus 10 times negative 26 plus negative 41 times negative 46. So I believe that is going to be 2058. Okay. So there's my dot product. My magnitude of n1 square root 2 negative 10 negative 41. So 2 squared plus quantity negative 10 squared plus quantity negative 41 squared. When I'm putting these into my calculator, I don't include the negative signs in there because I know that those negative signs are going to disappear. And I want to kind of make extra sure that I get those positive numbers in there. I'm just including negative 10 in here just to show you where it's coming from. But we've already mastered getting the magnitude of these vectors, right? Okay. Magnitude of that second vector. Negative 44 squared plus negative 26 squared plus negative 46 squared. And this one is going to be 4,728 root. Okay. We can take all that information, right? Dot product, magnitude, magnitude. Plug that into our equation. Say cosine of theta is equal to 2058 divided by these roots. Last thing to do is to take the arc cosine or inverse cosine of everything on there. That's something I'll take care of in GeoGebra, but I end up with around 44.9 degrees. This is asking for the dihedral angle that's smaller of the two. Theta will always give you the smaller of the two dihedral angles, right? Like that's back when we were using this to find the angle between two vectors, it was the smallest angle between two vectors. So you should never be getting something like 150 degrees from this. But Yeah, that's what they're asking for, the smaller dihedral angle in degrees, so that's what we got here. Okay, same process as last time, just now we had to do it to 2 planes and then apply it. Right? A lot of good skills in here. Right? Okay. This one is an interesting problem because I think most of the difficulty in it is revolves around trying to figure out where these points are. And I'll say this, if you're somebody who looks at these and you can visualize exactly what's happening, you see the cube, you can sort of rotate it in your head, and you can picture what this might look like from the top and the side and bottom view, and sort of intuit these, that's great, right? I have a lot of really, really bright students who are just unable to parse what's going on in a drawing like this. So what I'm going to show might be a little tedious for some of you, but hopefully I'll be helping out people that aren't immediately sure what's going on with something like this. So the goal here, it says the corner outlined in green is cut off the solid rectangle. If they tell you the y coordinate of A, the x coordinate of B, and the z coordinate of C, what's the equation of the plane of the cut off surface here, right? So this plane here, right? So we could figure out what's a normal vector sticking out of that, what's a point on the plane. Just like the previous problems, we're just figuring out 3 points. Once we have those 3 points, it's 3 points on the plane, identical to the problems we just did. Okay. So in terms of figuring out the coordinates of these points, I'll just kind of put some placeholders here. All right, so we know we're given some information about the y coordinate of A. So I'm just going to put that in there. I'm going to say the y coordinate's 1.5, the x coordinate of B is 3, and the z coordinate of C is 2.5. Okay. I think it's helpful to think about with this cube, and you had to do this a little bit on the previous quiz. This point here on the cube is 0, 0, 0, right? 0 in the x direction, 0 in the y direction, 0 in the z direction. We call that the origin. But what they're making here is, if we kind of extend the lines of this here, what they've created here, they say cutoff part here is you've got a cube, and then that cube is being cut off at a certain point here. So it's also helpful to think about maybe what the coordinates of this point here, like the corner of it before it's been cut off. The coordinates of that cube are well, 1 by 1. 7 in the x direction, 4 in the y direction, and then this cube is 3 units tall, right, in the z direction. The way that I want you to think about this is traveling from the origin to get to that point, right? So we traveled sort of along the positive x direction, right? We're traveling 7 units. And then along the y direction, that's this direction here, we're traveling 1, 2, 3, 4 units, right? In this direction here. And then we'll travel 1, 2, 3 to get to this point here. Right? So that's not A, B, or C. That's just kind of like the path that you can think of that we take to get there, right? But break it down x, y, and z. Okay. So let's look at point C first. So C, they're telling us it has a z component of 2.5, but if we travel 7 in the x direction, the y-axis is over here, so 7 in the x direction, 4 in the y direction, and then it's telling us we don't go all the way up to 3, we go to 2.5 here. So traveling x, y, and z, we can see that these are, this is 7, this is 4, this is 2.5. B is a point, so I'm going to start with the, how about I start with a z this time? So I'm trying to get to B, I'm going to start at the origin, and I'm going to travel up 3. Okay, so I'm traveling 3 in the z direction, there's my 3 there, and then I'm going to travel 4 in the y direction, right, from here to here, that's 4. So 4 in the y direction, and then they're telling us that I don't travel the full 7 to get to that corner. I just have to travel 3 to get there. Okay, and then A is going to be, let's do it this way. Let's say we travel 3 in the z direction, 7 in the x direction, 3 in the z direction, 7 in the x direction, and then we just have to travel that 1.5 in the y direction. So hopefully if you're having trouble figuring out what these drawings are meaning, hopefully that cleared things up. Okay, so we have the points. Since we've already done this problem where we find the equation of a plane with 2 points, I'll refer you to that one, but just to give a rundown of how I might try to find this, I would find AB crossed with maybe AC, right? That would give me my normal vector, and then it looks like all my options are AX plus BY plus CZ is equal to D type problems. You will figure out eventually that this is so I believe this is the -5, -8, -40 will be the normal vector that you get. In this case, unlike the first one, you do have to check and see which of these numbers is going to be most appropriate for that. So because you've got these 3 options, you aren't just double checking when you find D on here. So use any of the points that you want, but when you check that D, you do have to distinguish, right? You do have to make sure that that D lines up with what you've got there. Okay, and for this one, it ends up being this first option here. Regardless, any point you pick, right? Okay. All right. This one is one I think needs a little bit of clarification with the formula that we used. So this is the distance between 2 planes. So I'm going to kind of lay out how I would do the work for this problem, and then I'm going to give you kind of a different formula to use that I think is a little easier to use. But this is, if you're getting the wrong answers, in your distance between planes practice problems, this is the one you should be doing instead. Okay, so plane 1 is negative 3x plus y minus 4z is equal to negative 6. Plane 2, negative 9x plus 3y minus 12z is equal to 5. So what you were told for your equation is that this distance between the planes is going to be equal to absolute value of d2 minus d1, right? First thing to note here, you cannot just take, let's call this one d1 and d2, right? You cannot just take these numbers as they are between two planes and compare the distance between them, right? Excuse me. If you do that, you're not following the equation as it's written out. So part of the equation, or part of that theorem, looks like this. AB plus BY plus CZ is equal to D1. That's your first plane. AX plus BY plus CZ is equal to D2. Notice that A, B, and C have to be the same between these two planes. So the first thing to do is to get these two planes to match up, right? Thankfully, since these are parallel planes, their normal vectors are going to be scalars of each other. So I could multiply this one by 3, and I would line up negative 9, 3, negative 12. I think the better option here is going to be to divide that second one by 3. So if I divide this one by 3, I end up getting negative 3x plus y minus 4z. So I'll just say what I'm doing here. So if I divide by 3, that's going to be 5/3. Okay? So now I'm matching up. Even if I decide to use this D2 and D1 here, I'll just put a cautionary note here. I'll say this absolute value of negative 6 minus 5/3 will still not work. So in the formula, it says that these planes have to be normalized, right? So what normalizing means is you have to take the magnitude of this normal vector. So, so I'm going to say, hey, this normal vector here, so that's the same between the two of them, is equal to negative 3, 1, negative 4. Right? That's my normal vector. If I take the magnitude of that normal vector, that's going to be 9 plus 1 plus 16. So that's going to be magnitude of 20 square root 26. Right? When you normalize a plane, what you have to do is divide everything here. So here's kind of the idea. You would take everything here, divide it by square root of 26. So square root of 26, square root of 26, square root of 26, square root of 26, square root of 26. Every single entry on here, right? And that's what's called normalizing it. Now you've got a normal vector that is also a unit vector, so that normal vector will have a magnitude of 1. I think that is unnecessary for these problems, right? If you are asked for a normalized plane, that's what they are asking for. But I think a better way to do this is to modify this formula slightly. So rather than divide everything at this point by square root of 26, you can simply just divide by that magnitude. At this point in the formula, right? So this value is fine, right? But you do need to divide it by square root of 26. So this is not the way that the formula is presented in the book, but I think that this, I'll just make a note here that says this eliminates the need to normalize the formula. So anyway, I'll proceed with the problem as I think you should, which is to say that that distance is going to be equal to -6, or sorry, we're doing d2 minus d1. Order doesn't matter though, right? That's why the absolute value is there. And then we're going to divide that by square root of 26. That ends up being, let me pull up my calculator. Okay, so we get 1.307. So there's our answer there. Okay. I would modify your notes to include this. I think this is just the easier way to think about it, but also an important step. Make sure that your two A, B, and C values match up for the plane. Okay. This next one gets at something that I've been sort of harping on for a while, which is the difference between a scalar and a vector, right? So just as a list, before we get into what it means to be meaningful, I'll just kind of ask you to play along with me, right? When I say if A and B are vectors, if I say A dotted with B, we know that that's a scalar, right? And if I say A cross with B, we know that's a vector, right? When we get A dotted with B, That gives us a number like 32. This gives us a vector like -3, 9, -3. If I take, let's say, A plus B, you can think about whether that's a scalar or a vector. But yeah, if you add two vectors together, the result is this vector, right? Or you could think of it as 1, 1, 1 plus 2, 2, 2 is equal to 3, 3, 3, right? So vector plus a vector is equal to definitely a vector. Okay. We can think about let's say A, so this is like a scalar plus another scalar. That's fine. But if I say something like this, right? I've got a scalar and then dotted with, right? So this is a dot product here, right? So if it's C dotted with A, you say this is nonsense, right? You can't take a scalar and dot it with a vector. A dot product is between two vectors. If I want to say this though, that's totally fine, right? C multiplied by A, that's totally fine. That is a, that's like 5 times 1, 2, 3. That gives us a vector. Okay. Similarly, if I say something like two scalars together, right? This is a nonsense. So let's figure out what's nonsense and what's not. So the way I'm going to go through this is I'm going to talk about a vector, right? Here, so anytime I see a vector, I'm going to highlight it in green here. So this is definitely a vector. This is a vector. B plus C is a vector. B plus C is a vector. A is a vector. C is a vector. Okay. I think that's all the vectors. And then in purple, I'm going to write all the all my scalars are going to be in purple here. So that's B dotted with C, A dotted with B, this, 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 and then magnitude of the vector A is also a scalar. Okay, so let's run through this. A vector crossed with a scalar? No. A vector crossed with a scalar, you have to have cross product happens between two vectors, and I'm going to assume this means cross product here, so definitely not. Same exact thing happening here, scalar crossed with a vector, not going to happen. This one, scalar crossed with a scalar, no, we need scalar, we need vector crossed with a vector, right? Cross product is between two vectors, not two scalars. So this is actually a little debatable. I'm gonna have a little meeting with you could think of this as maybe like a one long vector. Anyway, I'm gonna talk with people about that. Dot product. So we've got a scalar plus a vector. Now a computer would, if you said something like 2 plus 1 1 1, like I think AutoCAD, so this is like a scalar plus a vector. AutoCAD might be generous and say, well, this is hurting my programming brain. Maybe I'll just convert that to a vector, right? But that's just a sort of nicety that certain programs will do. But yeah, in its current state, doesn't make any sense. Vector cross to the vector, that's great. Scalar times a vector, that's this sort of situation here. That's totally fine. So the official answer I'll give for this one is that we've got V and, 5 and 6. Those are the only valid ones. Okay. This one here, just more of a trivia. This will be the last one that I go over. But remember that if you want to find the area of the parallelogram, that's going to be the magnitude of the cross product of two vectors that you use to make it. They have not told you two vectors, they've only told you 3 vertices on it. Same technique as last time, right? Here's 3 points, A, B, and C. You figure out the vectors that are caused by those points, cross product of those vectors. That's for a parallelogram. Triangle is 1/2 of that. Okay. All right, that should be enough to allow you to solve all of the problems from 1.4 and 1.5. Next time we meet for lecture, I'll go over 1.6, which is a very short section on lines. But that'll be everything I'll need for quiz 3. And then we'll spend time preparing for the exam that you've got at the end of the month. All right, we'll talk to you soon.